Hey there. In this lab, we're still looking at energy, but we're also looking at work. Remember that we have three forms of energy that are part of mechanical energy, which we can calculate. One is kinetic energy, or 1/2 mv squared. The other, gravitational potential energy, which we can calculate with mgh, where g is our little g of 9.8 meters per second squared. And h would be the height or a change in vertical position of an object as it moves. And also we have our spring or elastic potential energy, US, which is 1/2 times k, the spring constant, times x squared, where x is how far you stretch or compress a spring. In this lab, we're not going to have a spring or elastic band, but we will have gravitational potential and kinetic to think about. We're also still looking at work. Remember that work changes the energy of an object. Essentially, work is just force times the distance over which that force acts on that object. In this particular lab, you're going to need to predict the velocity or determine the velocity of this green cart. We'll use energy conservation to assume that no energy is lost in our system as our cart speeds up from rest and travels down this track. With energy conservation, assuming the beginning energy is the same as the final energy of our system, you should be able to use a V in the kinetic energy equation 1/2 mv squared to solve for that v and see what the velocity of our cart should be when it gets to the end of the track. Work's going to be done on our cart by this force of tension in the string. So there's both work and energy conservation happening in this lab. After you make a prediction or a determination about what the velocity of this green cart should be based on energy conservation, we're going to go back and look at some other data, which you'll collect from this video, and actually calculate what the true final velocity of this car is when it gets to the end of the track. If you get pretty much the same number in your prediction for velocity and the actual calculation of it, then it stands to reason that, yeah, we probably conserved all of our energy there. If you get a significantly different value, say you predicted 5 meters per second, but when you actually calculated it from the raw data, you got only 4 meters per second for the final velocity of the cart, that would indicate that we didn't conserve all of our energy in the system, and it might have been lost or dissipated somewhere, somehow, to the environment. Let's take a look at our setup. Here's the big picture view of our setup. We have a dynamics track lying flat and horizontal on the table, and we have our green dynamics cart over there. I have it flipped upside down so it won't slide down the track. We're going to assume that there's no friction here. That's one of the reasons we can assume that all the mechanical energy is going to be conserved during this scenario. You can see that the dynamics cart is connected via paper clip and string, as we've seen before, all the way to the end of the track, where the string goes over what we'll consider to be a frictionless, massless pulley. We don't have to worry about the pulley. It's just changing the direction of the string. At the other end of the string is a mass that you can see is hanging stationary here right now. When we flip the cart over, it's going to be able to roll down the track. Because it's frictionless, it doesn't matter how small the weight is here. Any amount of weight is going to make that car speed up and go down the track. Our weight's going to fall to the ground, accelerating as it goes down, until it hits the ground. You can see that our cart's only going to be moving horizontally. So its gravitational potential energy is not changing. The only thing changing about our cart is going to be its kinetic energy, because it's going to speed up. However, also part of our system is this hanging weight. And right now this hanging weight does have energy. It has gravitational potential energy. And we can actually figure out exactly how much if we were to measure the height above the ground that the weight is currently positioned. That's a measurement we will end up taking. As the weight falls, its gravitational potential energy is converted into kinetic energy. And because it's attached by a string over to the cart, that gravitational potential energy from our weight is also partly transforming into the kinetic energy of the cart. Again, we're assuming that the total mechanical energy of this entire system is going to be conserved. So all the energy we're starting with, that gravitational energy right there, is going to be equivalent to all of the kinetic energy we end with. And we'll have some kinetic energy in our cart as it slides down the track. And we'll also have a final velocity and final kinetic energy for our weight as it falls. Again, our objective is to predict what is the velocity of our cart, and then we'll take a few more bits of data so that we can actually calculate what that value is. Let's start off taking some measurements. Right now we're going to take a height measurement right here to see how high our weight is above the floor. This height measurement is the h we can use in our gravitational potential energy, and we can say how much energy right now this weight has before we release the car and let both of these objects in our system speed up. As you can see, as the car is moved along the track, our weight is going to lower. And we'll have a picture on the screen of the direct measurement of our height of the weight above the ground. So there's the weight just touching the ground. And you can see, if you like, the actual measurements here on the track. So you'll see a meter stick of what the height of the weight is. But here's the final position of the front of the car on the track. And then let's go and see what the initial position of our car is. Our distances for how far the car travels and the distance for how far the weight travels should be the same because they're connected by a single string. There's the starting position of our cart. Right on there. Now we'll go ahead and take mass measurements for the two objects in our system, the hanging weight, and then we'll also get the mass measurement for our cart. That's pretty good. So here's the mass of our hanging weight, that much, plus we also have that guy right there. All right, let's take a look at our cart. Oh, that's not enough. There we go. All right, here's our cart. Got that. The back mass is at 0. And then there's the front one. Okay, now we're going to get a little bit more data just by watching the weight fall. As soon as we start to see the weight to move, that'd be the time to record, say, an initial time on our slow motion stopwatch. And then as soon as we see the bottom of the weight hit the floor, then that would be the time to record a final time from our stopwatch. And if we have a distance there and we know the initial velocity of our whole system is 0, this can be a way that we can use the data and maybe some kinematics to confirm or disconfirm our predicted velocity from energy conservation. Okay, I've attached the weight, but I've not let it go yet. 3, 2, 1. I'll do the same thing again, but by releasing it just by letting go of the cart. There's our weight. 3, 2, 1. do one more. And then we'll switch to overhead view. 3, 2, stop swinging. I've drawn out the start and end positions on the board. Those positions you could have gotten earlier when I zoomed into the track. We're basically looking at the same thing we just saw by watching the weight fall, because the weight's going to fall a vertical height which is equivalent to this same distance that the car travels horizontally. So this is another way to try to get the final velocity of our car and compare it to our energy prediction. We know, for instance, that this car, just like the weight, is starting from rest, so that tells me the initial velocity. Notice I have it lined up at the starting line, but because of the angle of the camera being that way, it actually looks like it's a little in front of, but this is actually lined up exactly on top. Over here you see the ending position. You see there's a little red dot on the actual measuring tool of the track. That white strip of paper is the meter stick, basically. That's lined up with the red line down here. So you can see there's actually a bit of an angle from the camera that's going to make it, maybe makes this a little harder to get an accurate final velocity. So it might be better to look at just the height of the falling weight to try and get the final velocity, because the final velocity of the falling weight is going to be the same as the final velocity of this cart. And that's what we're trying to compare to the energy prediction by using conservation of mechanical energy. So we'll do a few trials of this, just like we did with the falling weight, to see if we can calculate the final velocity this way as well. And then we can compare it to our prediction from energy. All right, 3, 2, 1. Three, 2, 1. As far as how we can calculate the final velocity, I suggest looking at a kinematic equation, perhaps one that does not have acceleration in it, though you could go and find that acceleration. That's possible. All right, let's do a last trial. 3, 2, 1. All right, let's think about this for a moment. In our system, if we did an LOL diagram for what just happened, you might say, okay, we've got a cart in there, we've got a hanging weight in there, And we're also going to have to include the Earth because the gravitational potential energy of my falling weight matters. So I'll put the Earth in that system too. In our LOL diagram, we always have on the x-axis K, UG, and US to show how much of each form of mechanical energy is present. We're saying there's no friction, and we're going to assume that mechanical energy is conserved. And one way we can write that is to say E for energy initial is equal to E final. So however much energy we start with, we're going to assume that's what we're going to end with. On the left side, this L represents when my cart is stationary and my weight is also stationary, but it's about to start moving. And so that's when the weight is at its highest height. On the right side over here, this represents right as the cart gets to the end of its motion, at its final position. This is also right when the weight is about to hit the floor. And so they both have the same velocity because they're connected. And it's a non-zero final velocity. They started with an initial velocity of 0, but now they're moving. And they're both moving. Both parts of the system, the cart and the weight, are moving. So that's beginning or initial, and then end or final. At the very beginning, nothing's moving. So we don't have any kinetic, and we certainly don't have any spring or elastic potential. Let's say that our weight has 5 blocks of energy that I'll draw in that left L diagram. Well, what happens when we go over here to the end? The gravitational potential of my cart hasn't changed. My cart's just traveling horizontally down the track. But the gravitational potential of the weight, which is all we ever started with, all of that has now been transformed or changed into the kinetic energy of the moving cart and the moving weight. So now I don't have any gravitational potential left. And I certainly don't have any spring or elastic because we never did. All the kinetic I have at the end, if we're assuming that our initial and final energies are the same because of conservation, then I should still have 1, 2, 3, 4, 5 blocks. Did I actually draw 5? 1, 2, 3, 4, 5. Yeah. So that's all we're saying here is all the initial energy is equal to the final energy. And I say, what initial energy do I have? I have all gravitational potential energy, and I could put an I there to be like, that's the initial gravitational potential energy. That's going to be equal to all of the final kinetic energy that we have. We have to be careful now at this point because we have to be careful what we substitute in for our gravitational potential at the beginning, or initial, and what we substitute in for our kinetic energy at the end, or K final. Initially, all that gravitational potential energy is possessed by this hanging weight that's just hanging there. So I'd say this is mgh, but maybe I'd call it mw for the mass of my weight, as I've called it in my system diagram. The mass of my weight times little g multiplied by the height it is above the ground. And that h always represents the change in vertical position of something. So we're going to call the floor the 0 line, and we measured with the meter stick how high the bottom of the weight is above the floor. We can also see that distance or height reflected in the distance that the cart travels, because the cart travels the same distance horizontally as the weight travels vertically. That distance is our h. Remember, we want g in meters per second squared if we're calculating. We want mass in kilograms. We want a height or distance in meters. The kinetic energy that we have at the end is actually split up amongst 2 objects. We have 2 objects in our system that are moving. I might say that one of these boxes of kinetic, that belongs to the kinetic of the weight. Because the kinetic energy of the weight is going to be 1/2 mv squared, but it's the motion of the falling weight. And maybe I say that these other 4 boxes of kinetic energy that are left over, these represent the kinetic energy of my green cart. So that would be the kinetic energy of my cart. So when we talk about all the final kinetic energy of our system, my cart is much more massive. And remember, kinetic energy is 1/2 mv squared. Both the cart and the weight have the same velocity v, but the cart has a much larger mass, as we saw in the triple beam balance. So I can say the kinetic energy of my cart is going to be more than the kinetic energy of my weight. But they both have kinetic energy at the end because they're both moving. And we know because they're connected by a string that they have the same velocity at the end. Let's see where this takes us mathematically in this equation. We've got kinetic final. I need to write in the kinetic of my cart plus the kinetic energy of my weight. They both have kinetic energy. The left side of my equation is still the same. I get the mass of my weight times little g multiplied by the height, or vertical distance it travels. Kinetic energy of my cart, remember kinetic's 1/2 mv squared, but this is going to be, I'm going to call it mc, the mass of my cart. Remember we took two different mass readings. Multiplied by the velocity squared. We got to remember our velocity of our cart is going to be the same as the velocity of our weight because they're connected. Plus, now I need the kinetic energy of my weight, 1/2 times the mass of my weight, mw, times the velocity squared. So if we're trying to use energy conservation, as we're depicting here, to solve for the velocity, we're going to predict what's the velocity for our cart, which is the same as the velocity of our weight when they get to their final position, and all that gravitational has been transformed into kinetic. We need to solve for v. So there might be some common terms I can factor out here. There might be some, maybe something cancels. But we want to solve this equation for v, and then we're able to make our prediction about what the velocity of our car or weight should be when it gets to its final position. When it gets to calculating the actual velocity of our cart or weight, there are a couple things we could do. We do have our time, and we do have distance values, or displacement. So we've got t, we have delta x, we know the initial velocity, and remember the velocities are always the same for the weight and the cart because they're connected, but the initial velocity, vi, we know that's going to be 0. And so we only have a couple other kinematic quantities we could possibly solve for. The final velocity, vf, which is what we want to know. Or you could try to figure out the acceleration. Which is a. So when we go to see what our actual velocity is, you could look at the time values we collected either by looking at the falling weight data or by looking at the horizontally moving cart, see how long it takes to travel a certain distance, delta x, or we could also write that it's the same as our h, right? That's the same thing. The initial velocity we know is 0 because we start from rest. So you could use these three pieces of information to directly calculate your final velocity. You can also figure out what the acceleration is. It's up to you how you want to go about doing that. But once you get a value for the actual velocity, which would be your vf here, we want to compare that to the prediction made by using conservation of energy and try to draw a conclusion from that.